Hello, this is Callie Daniels, and in this video we will look at applications of rational expressions. Well, remember our six-step process for solving an applied problem. We're going to read carefully, then assign a variable to represent the unknown value, use diagrams and tables and/or pictures as needed. If necessary, express any other unknown values in terms of the variable. In step 3, we'll write an equation using the variable expression or expressions. Then we will solve the equation, state the answer, does it seem reasonable, and lastly, we'll check the answer in the words of the original problem. Well, let's prepare to solve work, rate, and time applications, and start with a note. If a job can be completed in T units of time, then the rate of work is 1 over T of the job per unit time. Well, let's make some sense of this. In example A, it takes Tanya 3 hours per evening to complete her homework. Thus, her rate of work is 1/3 of the job per hour. That is 1 over the time it takes is 1 over 3, or 1/3 of the job per unit time, in this case per hour. In example B, Jim can complete the job of mowing his lawn in 4 hours. Thus, his rate of work is 1/4 of the job per hour. And that comes from 1 over T, in other words, 1 over 4. And we would say that's 1/4 of the job per hour. So just take the total amount of time and write 1 over that amount, invert it. Well, let's continue to investigate here. The amount of work completed is equal to the rate of work times the amount of time. We use W to represent the amount of work, R for the rate, and T for time. And you might say, well, this looks like our distance equal rate times time formula, and it's pretty much the same thing. In the D equal RT formula, the work completed is a distance that's being driven. Well, let's come back to example A and Tanya, who works for 2 hours, and her rate from our previous note is 1/3 of the job per hour. How much of the job is completed? Well, the amount of work is rate times time. Her rate is 1/3 of the job per hour times 2 hours. In other words, in 2 hours, working at 1/3 of the job per hour, Tanya would complete 2/3 of the entire job. So we're just multiplying rate times time. In example B, back to Jim, his rate of mowing the lawn is 1/4 of the job per hour. Now he's going to work for 2 hours. How much of the job is completed? Well, you might just look at this and say he's going to get half of it done, isn't he? And that's true, because work is rate times time. Jim's rate is 1/4 of the job per hour. And if he works for 2 hours, then he will complete 2/4, or you might say 1/2 of the job. Now, just to make sense of this, regarding this problem and Jim mowing the lawn, in 1 hour, he would complete his rate 1/4 of the job per hour times 1, or 1/4 of the job. In 2 hours, he would complete his rate 1/4 of the job per hour times 2, or 2/4 of the job, and we just noted that previously. We could also call that 1/2. And just continuing to investigate, in 3 hours, he would complete 1/4 of the job per hour times 3 hours, or 3/4 of that work of completing mowing the lawn. And lastly, notice that in 4 hours, he would complete 1/4 times 4 That's 4/4 or 1 entire, or you might say whole job. So if his rate is 1/4 of the job per hour and he works for 4 hours, he's going to finish mowing the lawn, isn't he? He must have a rather large lawn. Well, I think we're ready to look at an example. Here we go. Solving a problem about work rates. Al and Mario operate a small roofing company. Mario can roof an average house alone in 9 hours. Al can roof a house alone in 8 hours. How long will it take them to do the job if they're working together? Now, the thing you don't want to do is average their times. You know, the most common mistake I'll see made is someone will say, oh, well, we'll just take 9 and add it to 8 and divide by 2. You know, that's 17 halves or an 8.5. Oh, it's going to take 8.5 hours to do that working together. But that doesn't make sense, does it? If Al can complete the job in 8 hours working alone, it isn't going to take more time if he's got somebody working with him. Okay, so don't do that. Don't make that mistake. Okay, rather, let's let T equal the time it takes for Al and Mario to complete the job working together. Mario can complete this in 9 hours, therefore his rate is 1/9 of the job per hour. Al can complete this job alone in 8 hours, so his rate is 1/8 of the job per hour. Let's get the rates in there. We've let T equal the amount of time working together. That's T for both of them because they're going to start and stop together. Okay, so the amount of time is the same for both. Remember that work is equal to rate times time. So the amount of work done by Mario is 1/9 times T. And the amount completed by Al is 1/8 T. And together, when we add these or combine them, they're going to equal 1 whole job. Now let's write our equation. The amount of work completed by Mario is 1/9 T. Added to the amount of work completed by Al, that's 1/8 T. Together, those equal 1 complete job. The hard work's over with. We've got our equation. Now let's solve it. And I'd like for us to start by eliminating fractions. If we multiply through by 72, which is a lowest common denominator, when we consider the denominators 9 and 8, make sure we multiply each side by 72, and this is going to eliminate those fractions as we distribute. 72 times 1/9. Okay, well, 9 divides into 72 8 times. That product is 8T. And 72 times 1/8 is 72 over 8. 8 divides into 72 9 times. On the right, we have 72. Adding 17T is 72, and then dividing by 17, we could say that T is 72 17ths hours. Okay, this is a time in amount of hours, or you might want to divide 72 by 17 and write this as a mixed number. So that's a 7 right there. Got a little bit ugly. I believe that's going to go in 4 times. 4 times 7 is 28 and a 6. Difference is 4. We could also say that that time is 4 4/17 hours. If you want to write that answer as a mixed number. And notice that this makes sense. Okay, it's a little more than half of 8, which is the amount of time that Al can complete this job working alone. Just as a quick check here as we think about our step 6 of the process. If we substitute 72 17ths for T in our original equation, 1/9 times 72 17ths plus 1/8 times 72 17ths, is that really going to equal 1 complete job? Well, 9 divides into 72 8 times, so the amount of work completed by Mario is 8/17 of the job. 8 divides into 72 9 times. The amount of work completed by Al is 9/17 of the job. And adding in the numerator, we do get 17/17, which is 1 complete job. And this is going to check out just fine. Let's work a second problem. Here in example 2, we're going to again solve a problem about work rates. An inlet pipe can fill a swimming pool in 9 hours, and an outlet pipe can empty the pool in 12 hours. But through an error, both pipes are left open. Fatal error, huh? How long will it take to fill the pool? Well, once again, we'll let T equal the amount of time it takes for both pipes to fill the pool working together. That's kind of an interesting way to say it. As we think about this visually, let's say this is an above-ground outdoor pool, and we've got the inlet pipe filling, and the drain was left open, so it's emptying at the same time, trying to get this full of water. Well, our variable is T for both because they start and stop at the same time. The rate of the inlet pipe will be 1/9 of the job per hour, and the rate of the drain, the pipe emptying the pool, 1/12 of the job per hour. The amount of work completed by the inlet pipe is rate times time, so 1/9 times T. And the amount of work completed by the outlet pipe is the product 1/12 T. Okay, and together we need to see this one complete job. Okay, but this problem's going to be set up a little bit differently from our previous one, because the amount of work done by the inlet pipe, 1/9 T, and the amount of work done by the outlet pipe, 1/12 T, aren't going to be added together, rather subtracted. The inlet pipe is filling, the outlet pipe is draining, so it's taking away from the work that the inlet pipe is doing, okay? But hopefully we'll see this pool still get filled, okay? So 1 complete job in the end. Let's see, as we look at 9 and 12, a lowest common denominator is 36. So let's multiply each side by 36 in this case to eliminate the fractions. Okay, eliminating those denominators. And don't forget to multiply the right-hand side by 36 as well. Distributing. 36 times 1/9. Well, 9 divides into 36 4 times. That's 4T. 36 times 1/12. 12 divides into 36 3 times, and that's 3T. 4T minus 3T is 1T. In other words, 1T or T is 36 hours. Okay. Well, it's going to take 36 hours to fill that pool, okay, if both pipes are left open. Let's check and see if this makes sense. Checking in our original equation is 1/9 times 36 minus 1/12 times 36 really equal to 1. Well, that's 4 minus 3. I'm just dividing here, denominator into that numerator. 4 minus 3, is that equal to 1? Yes, it sure is. And what's happened here is that that inlet pipe has done enough work to essentially fill the pool 4 times. Meanwhile, the drain or the outlet pipe has done enough work to drain it 3 times. Fill it 4 times, drain it 3 times, we end up with 1 complete job, or the pool finally being full, and hopefully someone goes out there and closes both of those pipes. All right, there you have it. These were examples in which we solve applications of rational expressions. Make sure that you are showing up, working hard, stay positive. Good luck on these.